Okay, so once again, good morning. So today we will take up the last topic in the syllabus, B trees. See, generally, our convention is whenever we come across the word the term B tree, we think that B refers to binary, but here B does not refer to. So you have to always represent B hyphen trees. So this is how you have to refer to these trees. So here B stands for balanced. B stands for balanced tree. It's not binary tree here. It's not a binary tree at all. So it is a tree. Tree in the sense here there is no restriction on the number of children a node can have. So in a binary tree there is a restriction. We all know node can have maximum or at most 2 children. So, but here that restriction is removed. So it's a general tree. So we will discuss more about that. So before actually we start discussion about MBA search trees and then followed by B trees, you need to have some understanding about what we call as how the data is stored. Okay. See, in primary memory or in the main memory and in the secondary memory. See, generally what happens is, suppose if the data on which your program or the program logic has to work, if it is small. So what happens is, you can see that, say for example, in a small college like us, say there will be around 300 employees. So including faculty and non-teaching staff. So I want to do some operations on our college staff data. So because there are only 300 staff, so we would have maximum of 300 records. So what we will do, so you can directly transfer the table which consists of 300 records onto the primary memory, and then you can perform all the operations. Okay. So here, because the data is readily available in the main memory, accessing will be fast and performing operations also will be very fast, because accessing the main memory is very fast when you compare with accessing the same data in the secondary memory. So secondary memory nowadays, mostly we are using solid state devices, SSDs, but earlier we used to use hard disks. So our HDD we call it as hard disk drive. So hard disk drives, they are almost 20 times lower when you compare with your RAM chip. So random access memory chips. So nowadays we are using DDR4 or DDR5 memory chips as RAM. So almost DDR5 is almost 15 to 20 times faster than your secondary memory. See, for example, if the same data, if it is stored in the primary memory, suppose if 1 millisecond time is required to access the data, if it is stored in the main memory. If it is stored in the secondary memory, so almost it takes 15 to 20 milliseconds. So that is, so accessing main memory is almost 15 to 20 times faster than accessing the secondary memory. So you know, if the data resides in the secondary memory, you have to transfer the data from secondary to primary, and then only your processor can access it. So your processor directly cannot access data from the secondary memory. So it's a time-taking process, and your processor has to sit idle until the data is transferred from secondary memory to primary memory. So that's why, so what happens is, there are some such techniques which are very good when the data resides in the primary memory. But if the data resides in the secondary memory, so one of the most important prerequisite is we should minimize the number of disk accesses. So if there are more number of disk accesses, what happens is, so for example, if some data resides in the secondary memory, so assume that there are two searching techniques, searching technique X and searching technique Y. So X if it requires 3 disk access and Y if it requires 5 disk access. Okay, even though Y is faster because it takes more disk access, so it is not preferred when the data resides on the secondary memory. So if it resides in the primary memory, so whether it is 3 or 5 doesn't make any difference, because accessing the primary memory is very fast. Whereas if the same data resides in the secondary memory, so if more number of access is to be made to the disk. So generally, the searching techniques generally tends to slow it down. So that's why what we do is the such techniques are broadly divided into two types. So some such techniques, they are useful, some searching and sorting both. So internal searching and internal sorting. Internal searching and internal sorting means they are useful only when the data resides in the main memory. So some techniques, they are known as external sorting or external searching. What do you mean by external sorting or external searching? That is, these techniques, their performance is good when the data resides in the secondary memory. Say, for example, you take Aadhaar database of India. So almost all our country population is 130 crores. So suppose assume that 100 crore citizens have already enrolled for Aadhaar. So 100 crores citizens records will be stored in the Aadhaar. So you cannot store at any point of time, you cannot store in the main memory. So all the other database, they'll be stored in a pool of maybe pool of hard disks. So hundreds of hard disks, they'll create a secondary memory pool, and in that they'll try to store. So here, what we have to understand is when you want to search, say I'll give a Aadhaar number or I'll give some name. I want to search whether the address of that particular citizen. So in a 100 crore database, so you require very efficient searching technique or very efficient sorting technique. So which can access the data in the secondary device, secondary storage device. So the number of access should be minimal. Minimal number of times it should access the hard disk, and then you should be able to retrieve the data. So those types of searching techniques generally will be more useful when you are working with huge databases or databases with huge size. So now, actually, now I'll try to bring one more important term into the picture here. Apart from the data structure, see, basically data structures deals with the type of the data that we want to store and the type of relationship that we want to establish among the data while storing. So why we have to establish this relationship? If you establish relationship, what happens is it allows us to easily perform operations. So already we have seen stacks, queues. So depending on the application, we organize the data and then we use it in the application for performing various types of operations. Now, similarly, so generally data structure always refers to primary memory. We assume that the data is available in the primary memory. But sometimes when the data is available in the secondary memory, either in a hard disk or SSD or a tape drive, something like that. So here what we have to understand is, so there also we need to establish some sort of logical relationship while storing the data. So that will be dealt by your database management system. So database management system, what it does is, so generally database management systems, they always tend to work only with secondary storage devices. Most of the times, the database means so huge data. So organizing the huge data and then performing the different types of operations. So that is what your database management system is basically why it is required in this sense. So it is required for storing the data, organizing the data, and for performing various types of operations like retrieving the data, inserting the new data, modifying the existing data, searching for the data. And then whenever I give a query, say for example, query is, I want to know the student with highest marks in the college or highest percentage in the market in the among all the 5 years. So I'll write a small query. So I'll give it to your database management system. It searches the entire database and then retrieves the final year student with highest marks in the college among all the branches. So, or I want to know the how many students have more than 10 backlogs. Say for some purpose, I want to know. So I'll write a small query. So it should search in the database and it should. So it allows us to retrieve the data in a desired form. So that is what your database management system does. So actually, I'll just give introduction about B-trees here. So we have only introduction about B-trees. We will not go into the details, only the definition part. Again, in your second semester, you have DBMS subject. In the DBMS subject, you will study more about B trees and request trees. So they are very popular among database management systems. Almost all data, whether you take SQL or some other database, all of them for internal storage of data, they use B trees or a modified version of B trees known as B plus trees. Okay, so you learn more about this in your next semester. I'll briefly introduce you about only introduction about B trees. So the basic objective of B trees is minimizing the number of disk access. That is one of the most important objective of B trees. Okay, so how it does that? It does that by using the principle known as indexed sequential access method. So what is this indexed sequential access method? So I'll try to explain briefly. See, for example, okay, I'll just try to take an analogy. First, using an example, I'll try to explain. Then I'll try to explain using the disk. Say, for example, you want to visit your friend's house. Say, assume that your friend stays in an apartment, in a apartment complex. So assume that you called her and she told so and so apartment, some XYZ apartment, and my flat number is 1102. So you'll go to that particular apartment. Now you see, one way of searching is you start from the ground floor. Okay, so you start from the ground floor. You check. Okay, you in the ground floor only say flat starting from maybe 100 to 105 are there. Say here, for example, you take, I just take some number you take flat number 203. So you can start from the ground floor. In the ground floor, 203 is not there. You can go to second floor. You can go to, so in the second floor, you can find 2. But the thing is, excuse me. But the thing is, what we have to understand is, there's another efficient way, rather than directly starting from the ground floor. What we can do is, so here, suppose if 2 represents the floor number or the maybe in which floor they are. So what we can do is directly you can go to second floor, and from here you can search for third floor. So this is more efficient and less time consuming. So now here we are using 2 as the index. So 2 we are using as an index. Directly we are going to second floor and there we are searching for. Okay. Now same is the case. Now if you take any standard textbook, so your standard data structures textbook. Now you are searching for B trees. So now you can what you can do in the last few pages, glossary or index of terms will be given. So you search in B alphabet, you search for B tree. So directly you can see, okay, B tree is in 615 page. So open the textbook in 615th page, and you can start searching from the beginning of that page, and you can find about information about B tree. So the last few set of pages, almost all the standard textbooks, they provide index. Using that index, directly you can jump to a page where you can find relevant information that you are searching for. So these are all indices. So same logic will be used in the B tree. What is this logic? So it is like this. Okay. Say for example, okay, I'll not go into the details of your hard disk. I've shared a very good video. So if you have some half an hour time, you just go through that video. So what is a track? What is a sector? What is a block? So intersection of tracks and sectors is known as a block. So generally, your secondary storage device is divided into secondary storage device. Secondary storage device is divided into some blocks. So every block will have a fixed capacity. most of the hard disk, uh, each block size, typical block size would be around 512 bytes. Okay, this 512 bytes. Now, what we have to understand is, say if you see your hard disk, say for example, I'll take a simple example. Assume that I want to store 100 employees records. 100 employees records. So each employee record, 100 records, and each record size is 100 bytes. So employee record means employee identity number, employee name, employee department, all that information. Just assume that 100 bytes. So for storing 100 records, each record size is 100. So totally, so 10,000, 100 into 100, 10,000 bytes are. Okay, am I right? So if you take the typical capacity of each block is around 500. Okay, so totally how many blocks are required? Okay, for making calculation easy, let us take this 500. Okay. So 20 blocks are required. So 20 blocks will be reserved for storing 100 records, employee records in the secondary memory. Okay. Now, if you use sequential access, say for example, I want to search for an employee with identity 1202. So this is the identity number of an employee. Now I want all the details about this employee. Now what your technique will do? First, so how the data is organized. So totally 20 blocks, 1, 2 up to 20 blocks. So first it accesses the first block. Say in first block, so each block can accommodate 500 bytes. So approximately 5 records. So first 5 records will be searched. Then if it is not there, 1202 is not there, then next to 10, next to so next to 5, next to 5, so on and so forth. So in each block, 5 records are stored. So it accesses one block of information will be transferred into the primary memory. It searches for this identity number. If it is not there, next block. So suppose if it is there in the 20th block, so totally 20 blocks have to be accessed. So it becomes very slow. Now, in order to improve the performance, what we can do is we can use indexed sequential access. What is this indexed sequential? The indexed sequential is, so we can store key value followed by a pointer. So this is the key value pointed to the location in the disk where this particular record is. Now what we will do, so I'll store all this, so key values along the pointers in one block. Okay, so here only, so this is the index. So in the index table, we will store the key value followed by pointer to the respective record in the block. So for example, block number 5 and then offset. So offset means you can suppose if this is block 5, after how many bytes this will not be record is stored. Okay, so now if I want to retrieve this faculty or employee information, so I open one, say in first block, all this table is stored. Okay, index table is stored. I'll retrieve this. So 1202, I'll search sequentially. In the same block, I can find this. So here pointer will be there. Using this pointer, I directly jump to this block and I'll transfer this block to the primary memory. So now you can see earlier in the worst case 20 block access were required, whereas here index block access, then followed by the respective block access. With only 2 block access, you are able to retrieve the data. So index sequential access method will be more preferable in the case of secondary storage or when you are using what we call as when you want to apply your searching technique on a secondary storage device or on the data that is stored in the secondary storage device. So this indexing, okay, here we have used only single level indexing, but when you store lakhs of records, one single indexing is not enough. So you have to increase the number of indices, multiple or multi-level indexing. We call it as multi-level. Multi-level means, so here first level of table, so maybe 1 to 100. So 1 to 100. So this information will be stored in block 1. So 101 to 200, block 2. So like this we will store. So now what we will do? if I want to retrieve information about 105, so block 2, you will go to block 2. In block 2, again, so 101, 102, like this. So I can go to 105. So here pointer will be there. Now directly we go to the secondary storage, okay, and then we will retrieve. So this is 2 level. So here first level, index block number will be, you can get the index block number. You can go to this block. So you can find where this particular record is stored, the address of this record. Directly go to this block and get and retrieve the information. So this type of indexing is generally preferred when large volume of data is to be searched. Small volume, you may not use all this. Large volumes of data, you need to use these techniques. Okay, so for such cases, B trees are more preferred. Okay, so B trees basically they provide what we call as indexed sequential access method. How they will provide? So I'll discuss about this. You'll only understand. So in order to understand the concept of B tree, so already I have shared the definitions of B tree. If you want, you can open your WhatsApp and see that. So I've written so first we need to understand the concept of M-based search tree. So B tree is defined in terms of M-based search tree. So first let us try to understand what is this M-based search tree. So M-based search tree, so or otherwise it's called as a multi-way search tree. M stands for multi. So here what we need to understand is, in order, see, generally binary tree, what is the disadvantage? In any node, we are storing only one value. Binary search tree or AVL key. If you are searching for less than 10, you are taking this path, and if it is greater than 10, you are taking this right chain path. Okay, for example, in each block, if you can store 5 levels, so after going up to 5 levels, suppose if the value you are searching for is not there between 0th and 5th level, now next level of tree you need to once again transfer from secondary memory to primary memory. So it requires more. As the height or depth of the binary tree is more, you require more and more accesses. So that is why instead of having only one node, one value in the node, in a multi-way search tree, what we are trying to do is, we are trying to have multiple values in each node. We are trying to have multiple values in each node. So by having multiple, so if you transfer this node from secondary memory to primary memory, simultaneously you are getting 2 values. If you are searching for a value less than 10, you can take this direction. If you are searching for a value which is between 10 and 80, you take this direction. And if you are searching for a value which is greater than 80, you take this. So simultaneously, you are able to compare with 2 elements. Okay. Otherwise, if it is a binary search tree, you require 2 levels. 10, first 80, then followed by 10. So you require multiple levels, and it also increases the disk access. So to minimize the disk access, here we are trying to have multiple values in each. Okay. So it's called as M-based search tree. So M-based search tree, so the nodes are divided into internal nodes and external nodes. So these are external nodes. This is an internal node. Okay, this is root and this is internal node. So one of the root is also an internal node. So node with children is known as internal node. So leaf node is known as external node. Okay, this is external node. So generally, external node in a B tree does not have any special meaning. So null pointers will be replaced with external nodes. These are all null pointers. External nodes, they represent null pointers. So now, internal node, it can have m children and 1 to m minus 1 elements. What is this? You try to understand carefully. If you take any internal node, say for example, if I take m as 3, so that is, it is a 3-way tree. So 3-way tree, internal node can have maximum m minus 1. What is m minus 1? 2. So it can have 2 key values, okay, 5 and 9. Okay, so it can have 2 key values. And what is this 3-way means? It can have 3 ways of searching. So this subtree contains all the values less than 5. This subtree contains values greater than 5 and less than 9, and this subtree contains all the values greater than 9. Okay, so this is how, so Now, generally, two types of B trees are very popular. Okay. So one tree is called as 2-3 tree, and another tree is called as 4-5 tree. What is this 2-3 tree and 4-5 tree? So 2-3 trees, node can have 2 keys and can have maximum of 3 children. Node can have maximum of 4 keys and it can have maximum of 5 children. So this is a 2-3 tree. So why it is a 2-3 tree? Node can have maximum of 2 keys and it can have maximum of 3 children. Okay. So internal node, if it has m minus 1 elements keys, then it can have m children. Okay. So now what is this? Already I told you. So in any internal node, if you store p elements, then it should have p plus 1 children. So here 2. Say for example, if I take 4 here, okay. So K1, K2, K3, and K4. So now, so how many children it can have? All the values less than K1 here, all the values greater than K1 and less than K2 here, all the values greater than K2 and less than K3 here, greater than K3 and less than K4 here, and greater than K4 here. So 4 keys and 5 children. So this is a 4-5 tree. This is known as 4-5 tree. Okay. So now this is about this. Now all the values, whatever you are storing in the internal node, they should be in this order. They should be in a sorted order. They should be in the ascending order. You can see you have to write it as 5 followed by 9, not 9 followed by 5. You can see here 10 is less than 80, 2 is less than 4, 4 is. So all these key values, okay, all these key values, just a moment. So all these key values, they should be sorted order. Okay. First one is m minus 1 elements. If you are storing m minus 1 key elements, then we should store m children. Or otherwise, if you store m keys, m plus 1 children. Okay, that is what the second point is. All the keys, whatever you are storing in an internal node, they should be in sorted order. They should be ascending order. You can see 20, 30, 40, 50, 60, 70, 82, 84, 86, 88. They are in sorted order. Okay, so a tree which satisfies these 3 rules is called as a M-way search tree. It's called as an M-way search tree. So apart from this, the same M-way search tree. So now we come to this B tree definition. So B tree is a M-way search tree. So say for example, you can have B tree of degree 2 or degree 3 or degree 4 or degree 5. So M, suppose if you take M as 3, what is the meaning of this? It is a 3-way search tree. This is an example. So node can have maximum of 3 children. That is what we mean by M. M3. So if you take M as 5, what is that? An internal node can have maximum of 5 children. That is the meaning of M. M-way search tree means, so how many paths it can have. So next property that B tree should satisfy is root has at least 2 children. So these 3 may not be satisfied by a M-way search tree, but all M-way search trees are not B trees. For an M-way search tree to be called as B tree, it should satisfy 3 additional rules or 3 additional constraints. One is root has at least 2 children. So B tree should have at least 2 children in its root. That is one thing. And internal nodes other than root have at least m by 2 seed children. Okay, at least m by 2. Suppose if I take m as 5, in a 5-way search tree, all internal nodes, how many keys it should have? So, sorry, it is children. How many children? Minimum number of children it should have 5 by 2 seal. What is 5 by 2 seal? So 2.1 seal. What is 2.1 seal? 2.5 seal? It is 3. So you have to round it off to next higher integer. So that is, so in a 5-way search tree, so if you want to call a 5-way search tree as a B tree, all the internal nodes should have minimum of 3 children. Should have minimum of 3 children. Then only you can call it as B3. This is the third rule. And external nodes are at same level. Now, these are the external nodes. All the external nodes, they should be at the same level. So, M-based search tree, okay, if the root, if it has minimum 2 children, and all the internal nodes, if they have minimum or at least m by 2 seal children, and if all the external nodes are at the same level, then such type of M trees are known as B trees. Now, this is an example of a B tree. So observe carefully. So this is an example of a B tree. Okay. Now you see. So in the root we have minimum 2 values. Now say how we have to proceed for search. Say for example, if I am searching for 40, compare 40 with the first key value. 40 is greater than 10. Compare 40 with 80. 40 is less than 80. So you have to take this pointer. So using this pointer, you have to reach this. So this is an index. So this pointer is an index. So this is an index to a set of values where you can search for 40. So directly with this index, you can go to this block. So here 20, 30, 40. So here, so this is the key value. Here, along with key, a record pointer will be there. So a pointer to the actual record. So where you can find all information about the record with key value 40. So that is, so in which block and at what offset. So information about 40 employee or 40 key value is available in the secondary memory. So record pointer will be there along with this key value. Using this record pointer, directly we go to the secondary memory into that specific block after, say, if it is after 100 bytes in B4 block. So in B4 block, we will transfer the B4 block onto the primary memory, and then after 100 bytes, we'll start searching the record, whatever we are looking for. That is how we search for. So now this is about here B trees. So okay, so B trees basically here you have multiple values. So in each node we are storing multiple values. Why? Because if you so all these values will be stored in a block. So when you transfer one block to primary memory, all these values will be available right directly. So if you use binary search tree, in one node we are storing only one value, so only one value gets transferred. After that, if you are searching for a higher value, next level node you have to once again transfer from secondary to primary. Again, it requires one more disk access. By having multiple values, you can decrease the number of disk access. So that is the advantage of B trees. Okay. So this is about B trees. Okay. So you please try to remember the M-based search tree definition and then B tree definition. So generally they will ask only the definitions, and then you remember this one example. You just explain it using this example. So node has 2 children, and then what is that? Internal nodes other than root have at least m by 2 children. So now what is m value here for this? What is m value for this binary tree? So here 1, 2, 5, 6 means, so it is 7-way search tree. So 7-way search tree. So internal nodes other than root have at least m by 2 children. What is m by 2? So 7 by 2 seal. What is 7 by 2 seal? 3.5 is 4. So other than root, all the remaining internal nodes should have minimum or at least 4 children. So if you take this, it has 1, 2, 3, 4 children. If you take this, it has 7 children. If you take this, it has 5 children. So all the internal nodes have more than have 4 or more children, at least 4. Okay, so at least 4 means 4 or more. So external nodes. So if you see all external nodes, they are at the same. External nodes, they don't represent any meaning here. So only null pointers will be replaced with external nodes.